So chapter number 1, structure of the periodic table 10.1. We discussed the structure of the periodic table as per to update you with the differences that we haven't carried forward from IGCSE or O levels. And that is IGCSE or O levels consisted of simple 8 groups, but this time we have changed it a little bit and we have the group numbers all the way starting from 1 to your extreme left to all the way over here. We have even numbered the transition elements in their columns to 18 for noble gases. So this is how we have changed the periodic tables learning for groups and periods. The groups remain the same. You can even put the group numbers in simple numbering, that's fine. You don't specifically need to go for a Roman numeral. That's completely all right. Now, the word periodicity might be used or periodic patterns might be used a lot in this chapter. So the recurrence of a same pattern, because it is repeated in a group, maybe sometimes in a period too. So for that, we use the term periodicity for the phenomenon and periodic properties for that specific property. Now, periodicity does not exactly mean that the pattern will be repeated with the same intensity or with the same strength. We do understand that for physical properties, the properties tend to change. They might increase, they might decrease, they might show a proper trend, they might show an improper trend while we are at it. So this is actually the table, and you already know about the lanthanoids and actinoids. 57 to 71 are considered as lanthanoids after the element lanthanum, and 89 to 103 are considered as actinoids after the element actinium. Now, these are transition elements. They are also known as rare earth elements. When we use the word earth in for a group or for a period, that means those elements are taken out of Earth's crust. Now, if we use the word rare, that means they're present in a very small quantity for the entire planet. There are some elements in here for which we haven't given the mass numbers. There are dashes present. That is because they may be man-made or invented instead of discovered. Some of them are radioactive and they might not have any stable isotopes at all. That's why there are dashes over there. So it goes all the way to the end of the period 7, and many of them are now named after scientists' dedications that we give them. Okay, so this is the latest accepted form of the periodic table, group numbers 1 to 18, period numbers 1 to 7. The transition elements are given group numbers 2. It's easy to change the old group numbers 3 to 8 into the modern form. You just add 10, 3 becomes 13, 7 becomes 17, so on and so forth. That's the easy part. Actually, what you're going to notice in these 4 chapters, 10, 11, 12, 13, we call them the inorganic portion of your book. They're mostly based on facts. And sometimes these facts might have an explanation. Sometimes these facts might just be interlinked to one another. And it might be just a portion of memorization or cramming at all without any further explanation to it. So 10.2, periodicity of physical properties. So starting with the periodic patterns of atomic radii, we can always compare the size of different atoms using atomic radii. Now, the data for these measurements come from elements single covalent radius. Now, what do? We consider two atoms joined together. We talk about the line joining the nuclei of one to the line joining the nuclei of the second, and we take the half of that distance as the radii. Overall, it must be diameter. So we consider radii most of the time. However, there are some past paper questions which might use the word diameter or the distance between the two elements as a word, though diameter is not the appropriate term for it. So distance between two nuclei or internuclear distance or internuclear distance, words like these have been used in past papers too. So there are other measures of atomic radii, such as metallic radii, ionic radii, van der Waals radii. However, covalent radii can be obtained for most elements. these provides the best data for comparison purposes across a period. The values of atomic radii for period 3 are given in table 10.1. We can see the pattern across the period more clearly. You have the table right in front of you. These are period 3 elements. We have started from sodium all the way to argon. And as you can see that the atomic radii are decreasing if when we move from left to right in the periodic table across the period, the atomic radius is given in nanometers 1, which is equal to 10 raised to power minus 9 meters. No data is available for argon. Actually, most of the time, the data won't be available for the noble gases. So that's how it goes. Remember, the data is not available for argon because covalent bonding won't be possible for argon. the But that doesn't mean that covalent radii, if that isn't possible, we can't go with any other radii. Don't forget that metallic or ionic or van der Waals radii can also be considered. So van der Waals radii data for noble gases is also present on the internet. So sometimes you might be able to find some data, and there are some questions in the data might be quoted. So going according to the examiner's point of view, don't keep a sort of opinion about it. Just keep an open mind. Now, the atomic radius decreases across the period because the increasingly positive nuclear charge pulls the electrons in the outer shell closer to the nucleus. I hope you understand this reason. Let's go through this. If we're talking about a period, remember the shell remains the same. If we're talking about period 3, we're probably talking about the third shell being filled. Now, if we're talking about the third shell being filled, you won't change the shell, so there won't be any changes in electron shielding. There won't be any changes in number of shells. You will just be filling in the protons and the electrons in the same shell. So the pull, the nuclear pull, or what we call the positive nuclear charge, which pulls the electrons in the outer shell, becomes greater and greater. So moving on from left, from the sodium all the way to right to fluorine, this radius decreases. I hope you understand the reasons. Again, the four reasons that we have discussed in the chapter 3, chapter 2, before that we discussed for even for ionization and for other patterns, we're going to stick to the same reasons. We used to talk about four different reason points. For example, the nuclear charge, the pull, of course, of the protons towards the electrons, atomic radii, which actually we have sometimes taken it as the distance of the outer shell electron and the nucleus. Atomic radii almost means the same thing. Then comes the third parameter, which was electron shielding. And the final and the fourth one was the type of subshell that was present, or either there were any unpaired electrons in that shell or not. So that subshell or not. So these were the four factors that we considered way back then in chapter number 2 and 3. And we're going to consider the same factors in these chapters too. So the atoms of noble gases in group 18, such as argon in period 3, do not have a covalent radius, as they do not form bonds with each other. The atomic radii can be determined from van der Waals radii, as I've already told you before. This is found by measuring the distance between nuclei of two neighboring atoms, touching atoms which are not chemically bonded together. The distance is divided by 2 to give the van der Waals radius. The figure will be higher than the single covalent radius of an element since there is no overlap of electrons involved in the van der Waals radii. So the atoms are not as closer as you might think. So the answers to van der Waals radii are usually greater than covalent radii. Why? Because there is no bonding. It's just a weak intermolecular force that is connecting the two atoms or brought the two atoms closer to one another. I hope you get the point, right?
Yes, sir.
Okay. So moving on, the atomic radius decreases through period 3. The same pattern is also found in other periods across the period. The number of protons to the nuclear charge and number of electrons decreases by 1 with each successive element. We've already explained that this extra electron added to the atoms of each successive element occupies the same quantum shell or energy level. I've already explained this too. This means that the electron shielding remains roughly constant. Attractive forces exerted by the positive nuclear charge or the increasing positive nuclear charge actually, since we're filling it step by step, so that pulls the electron closer to the nucleus, for which the atomic radius actually decreases across the period. That's how we can say it. Now, every time you're going to look at a graph, be it period number 2, 3, or period number 4, not considering the transition elements, you're going to find a decreasing line in a similar way. So the atomic radius would decrease from left to right in a periodic table. Okay, so moving on, ionic radii. Now, when we talk about ionic radii, we are actually trying to talk about both the ions. If we're talking about both the ions, then the whole scenario changes for both types of ions. I mean, I hope you understand already that positive ions are formed differently than negative ions. And of course, the radii for positive ions is going to be different than the negative ions. Losing an electron might cause you to lose the entire shell. Gaining an electron might cause the outermost shell to expand a little bit. So yeah, these facts are going to change everything for positive and negative electrons, positive and negative ions. So let's discuss this. Starting with the most important part, the ionic radius decreases across a period as the positive charge on the ion increases and negative charge on the ion decreases. This is because increasingly positive nuclear charge pulls the electrons in the outer shell closer to the nucleus. In the same period, negative ions have larger ionic radii than the positive ions because they have one more electron shell. So the outer electrons are further from the nucleus and there is more shielding. Now, this has discussed uh, uh, actually the positive ions and the negative ions all together. So what we are going to do is that we're going to take this table 10.2 and we're going to discuss the positive ions and the negative ions a little bit separately. This has to be done in detail. I want to make sure that you are able to compare not just the trend starting from the left of the period going all the way towards the right of the period, but you also are capable of talking about the contrast of any two positive ions or any two negative ions considered for the fact. Okay, so let's start with sodium ion. If I talk about sodium ion, I hope you understand the configuration of sodium atom is 281, which means there are two electrons in the first shell, eight in the second, and one in the third shell. Now, if I convert that into sodium ion, of course, that is by losing this electron. So we're left with just 2,8. Okay. On the other hand, if I talk about the chloride ion, as you know, for the chlorine, the electronic configuration is 287, and the third shell has 7 electrons. And this then converts into chloride ion by gaining 1 electron, so it's 288. Now, in this case, if you compare both of them, although they're in the same period, but I hope you understand that the negative ions have one more shell completely filled, probably, as compared to any of the positive ions in the same period. Any of the positive ions. Even if I'm going to consider magnesium, that's going to end up in the same way. Take a look. Magnesium is actually 282. It's going to lose 2 electrons, and that's how it would be converted into magnesium ion, which is Mg positive 2. But still, it's going to have 2,8 configuration. This is the configuration similar to neon, the nearest noble gas to magnesium. Now, if I consider sulfide ion in that case, the sulfur has 286. Now, it becomes sulfide by gaining 2 electrons. So sulfide in that case will have 288. So if you talk about any of these, for that matter, you will understand that the negative ions, as he's saying, have one more shell filled as compared to the positive ions. Okay, that's one piece of fact right there. The important paragraph, the box given above, has many other pieces discussed at the same time. So So this is one of those pieces of information. I hope you get the point. Now, if we consider this fact, then we should understand that for both of them, the electron shielding is entirely different. I hope this should make sense to you. Now, let me explain. For magnesium ion, these 8 electrons are only experiencing the shielding from these two. For sulfide or for chloride, the outermost 8 electrons are actually experiencing the shielding of 10 electrons, not just two. This works differently. So the electron shielding for the negative ions and the electron shielding for the positive ions for the same period is not the same. And we need to keep that fact. And this is another piece of information given in the important portion. And that's actually the last line. There is more shielding. Actually, if there are more shells, there definitely would be more shielding. Now, the last piece of information related to this. The second shell, which is completely filled in the positive ions, maybe this shell or the shell for magnesium and sodium ions respectively, is actually closer to the nucleus as compared to the outermost shell for negative ions. Now consider about chloride. This is the outermost shell, or sulfide. This is the outermost shell. Now that's not the second shell. That's actually the third. So the outermost shell is different for the positive and the negative ions. Since there is another shell introduced or completed, or at least stabilized if not completed in case of negative ions, so of course the shell would be distant from the nuclei, would experience more shielding, and would be different in number as compared to the positive ions. So everything changes. Now, we are not just here to talk about the differences in the formation of positive or negative ions or the valence shell electrons or which shell they just lie in. This is also about the trend. So we need to understand the trend. And for this kind of trend, as you can see, the numbers are totally different. You're going from 0.095, 65, 50, 41. Yeah, there is a decrease, there is a good decrease. And then there is a bump, 0.212. This is a huge difference. So in between 4 and 5, we're going to find a difference, actually a big jump. And then it starts decreasing again to 1, 2, 184, 181. It starts decreasing again, nice and smooth. So actually, the whole trend can be divided into two parts. Though it's a decreasing trend as a whole, but there is a jump in between. So what I'm going to do is that I'm going to discuss all the smaller paragraphs he has taken to explain the entire set of facts or trends. I'm going to go paragraph by paragraph right below this table. Starting from the first one, the positively charged ions have effectively lost their electron shell of electrons, third principal quantum shell or energy level from their original atoms. We're talking about sodium ion, we're talking about all the positive ions in there. For this reason, the cations are much smaller than their atoms. To add to this effect, there is also less shielding of the outer electrons in these cations compared to their original atoms. Okay, so if we going to compare to their parent atoms, they have one less shell and they have less shielding. Of course, they are closer to because the atomic radii, the ionic radii is now much less. They're closer to their nucleus as well because we're talking one step down for the outermost electron. Okay, so going across the period from Na positive to Si4 positive, the ions get smaller for the reason similar to those of decreasing atomic radii across the period. The increasing nuclear charge attracts the outermost or valence shell electrons in second principal quantum shell energy level closer to the nucleus with increasing atomic number. But that's not just it. Writing just these lines in your answer as an answer to a question in the paper is not going to cut it. You need to let the examiner know that every time we're talking about a step ahead from sodium to magnesium or magnesium to aluminum or aluminum to silicon, there's actually an increasing charge, which means the proton and electron comparison ratio are totally different. Let me compare that for you. And we need a more uh, spectacular or a pondering eye to understand the differences. Now, in the case of sodium, it's 11 protons and they are trying to attract 10 electrons, right? If I talk about magnesium, there are 12 protons and they are trying to attract 10 electrons again. 13 protons, 10 electrons. 14 protons, 10 electrons. Try and understand the fact that every time you're adding a proton, but the number of electrons after the whole losing electron scenario remains the same. So every time you step from left to right, you're actually attracting them with a stronger force of attraction because 12 protons to 10 electrons is a bigger ratio, bigger attractive forces. 13 to 10 ratio is even a bigger one, and it continues to silicon. Now, I've explained a number of points for the whole thing. I hope you understand the fact. Let me quickly repeat. I have been discussing mainly about four factors. First, they lose the energy shell, the outermost energy level. So that's why, secondly, they are smaller than their parent atoms. Third, they are going to have more shielding, less shielding, of course. And finally, fourth one is that the electron-proton ratio becomes greater at every time you step from left to right. Although they're all positive ions. So I hope you understand that you are supposed to answer this question with not just three facts, but four facts. And I've seen students considering the first three facts because that is a part of the book and they are too obvious since they're written in words. And the fourth fact is not written since the ratios are not written, so they never bother to discuss the ratios. So try and keep going with all four factors at the same time, right? I hope you get my point, right?
Yes, sir.
Good, good. Now let's talk about the rest. I mean, the negative ions. Negatively charged ions are larger than their original atoms. That is because when we add an electron to the quantum shell, to the last quantum shell, in this case, the third principal quantum shell, this actually increases the repulsion in the already present electrons. This repulsion is brought to a minimum or is stabilized if all the electrons actually go back a few notches and they try to change their place. They are repelled outwards. The shell becomes a little bit bigger after a little bit of expansion. So negative ions are actually different than the positive ions in that case. But what makes it more interesting over here is that group fifth is not the one that takes up one electron. It's the one that takes up three. The difference between the fourth group and the fifth group over here, I mean the group 14 and 15 over here, is actually a big jump because we are talking about the loss of four electrons and the ionic radius for that, all the way to the gain of three electrons, the maximum number of electrons possible in a period, in periods like these, would be a big jump. So gain of three electrons, uh, gain of three electrons, gain of two electrons, gain of one electron. Imagine one electron poses repulsion and the size expands for the shell in order to stabilize the shell a little bit. For two electrons, there would be even more repulsion, so the size would be bigger. And for three, it's going to be even bigger than that. And these are the differences that we can see. But we need to discuss other factors as well. So moving on, and I'm going to keep all of this, I'm going to just move it on. The negatively charged ions are larger than their parent atoms. This is because each atom will have gained one or more than one extra electrons into the third principal quantum shell. Remember, since we're talking about trend in period 3, that's why we're continuously talking about third principal quantum shell. If they talk about period 4, if they talk about period 2, you need to change this number as well. Don't just keep on going with the same number. Okay, so this increases the repulsion between its electrons while the nuclear charge remains constant. Okay, this increases the size of any anion compared with its atom. So these are the reasons why the size for anions is bigger than their parent atoms, and of course the trend is decreasing. Trend is decreasing because of the same set of reasons. Okay, so let's erase this part at least. Okay, now we are here with the graph, atomic numbers for entire period 3, left to right, and ionic radii. I hope you understand a decreasing trend. Then the big jump I was talking about, remember the jump is in between group number 14 and group number 15. These are not the group numbers, these are the atomic numbers, that's why. And then again, a decreasing trend. So overall, it's a decreasing trend apart from the jump because of the change of positive and negative ions. I hope this topic is completely clear to you. If it is, we can move on. So, assuming that the topic is clear and moving on, periodic patterns of melting points and electrical conductivity. Now, the book tries to discuss a certain set of periodic patterns, but remember, and if you're going to take a look at the past papers, they may go out of these specific periodic trends and can discuss an entirely different trend or a periodic pattern. And just by giving you the table, they can ask questions. And as soon as you look at a table, try to find a pattern. This is important that you do. Okay. Now, when you're looking at a pattern, you can work with increasing or decreasing trends. But sometimes in increasing or decreasing trends, you may find an anomaly. Anomaly is something odd, something different, something which is breaking that trend, but tends to continue before and after that element. We call that specific element as anomaly. Okay. So if we look at the melting points, yeah, the melting points are really different for these elements. Now, I hope you have discussed the melting or the boiling points back in O levels or IGCSE, so you do have the idea. Uh, if I don't even talk about the O levels, if I specifically talk about the IGCSE, there is a proper chapter, and at the end of the chapter, we have a small graph, or we had a small graph at least, if we go a little bit back into the years, which discusses the trend of melting point, which gives the student the idea why the numbers are so different from one another for period number 3 for melting point in Kelvin. I hope you understand that in the graph for that kind of trend, it was something like an increasing and then decreasing trend, something like this. And the peak was seen at group 4 in that specific topic back in O levels. So yeah, you will find an increasing trend all the way to the maximum over here. Then there is a decreasing trend, but we do find an anomaly right here. Okay, so that is a way to look at it. I'm still supposed to discuss it. I'm just telling you how to look at a table, even if the examiner comes up with something entirely different or new, how you can look at it and how you can perceive or find out the relation or a pattern between a given set of number in order to compare it to even a graph. If you can't just simply understand numbers and numbers are a little bit difficult for you, you can round off round them off to the closest 50s or hundreds, and then try drawing an imaginary graph. It would give you a very good idea what is happening over there, right? I hope you get my point. Let me say that again. If the numbers do not make any sense to you, you can round these numbers off to nearest 50s or hundreds, and then you can plot an imaginary graph for you right there, then and there in the paper. Don't just go with exact numbers. Try to plot an imaginary graph. Let's say this is 100, 200, 300, 400, 500. Try to go with these values with imaginary. If you have to write it as a baby steps, or when you're doing it for the first time, yeah, go ahead, write them out. But at second, third, fourth attempt, try doing it without writing anything. It should be a part of your imagination instead being a part of paper. But if you think you're going to make a mistake, make it a part of paper. I'm just asking you not to make it a part of paper to save you some time, because to put some lines in your imagination does not take time, but doing it on a piece of paper is definitely going to take time. Okay, so with this kind of imagination, it's much more easier to understand what the trend is going to be, instead of just perceiving numbers. If you're good with numbers, that's good enough. You don't need to go with this kind of exercise. It really depends upon what kind of personality are you. Okay, so moving on, period 3 element electrical conductivity taken in the units of S per M. Now we are going to discuss this, what that is. And you can also see the values over here. Of course, electrical conductivity for a period is going to be much different. Why? Because we start off with the metal, we move on to a metalloid, and then we start with the non-metals, moving all the way to a noble gas. The period is very different when it comes to metallic properties. And if we're talking about electrical conductivity, yeah, the values are supposed to change by bigger differences, which is completely understandable. Now, S stands for Siemens per M stands for per meter. Siemens per meter is a unit of electric conductivity. Okay, so that's why it has been considered. Now you can see the numbers. Let's discuss these values. Okay, starting with the first paragraph, the electrical conductivity increases across the metals of the period 3 from sodium to aluminum. Electrical conductivity then drops dramatically to silicon, which is described as a semiconductor, a metalloid 2, and falls even further to the non-metallic insulators, phosphorus to sulfur. Right. So if you move on to phosphorus to sulfur, this is going to drop more and more to, and of course, the gases cannot be discussed, so dashes with the gases. Okay. To explain the trend in melting points in electrical conductivity across a period, we have to consider the bonding and the structure of elements. Now that's important. Let's talk about period 3 in that way. This is going to joggle your memory and all of your information related to bonding chapters. Now, sodium is a metal which, of course, goes with metallic bonding. So does magnesium and aluminum. Silicon goes with, silicon is actually considered with, for SiO2's example, which is covalent and actually a giant molecular structure. Phosphorus has been considered for P4, sulfur has been considered for S or SH, both are the same example. Cl has been considered for Cl2. So simple molecular. So is Ar, since it's a monatomic molecule, a molecule that consists of single atom. Okay, so metallic, covalent, nothing. Okay, giant metallics, giant molecular, simple molecular goes on to simple molecular again. I hope you get the points about bonding and structure. Okay,
Yes.
so moving on, let's start with the extreme left. Sodium, magnesium, and aluminum at the start of period 3 are all metallic elements. As you saw in section 4.6, their metallic bonding can be described as positive ions arranged in a giant lattice held together by a sea of delocalized electrons. This is exactly the two-line explanation we give for giant metallic structures commonly. Now, the delocalized electrons are those from the outermost shell. They are free to move around the structure, within the structure, through the structure. So much so, whenever a potential difference, or by potential difference, he's actually trying to imply voltage is applied, the delocalized electrons drift through the material towards the positive terminal with the maximum speed, and that's how they are able to carry the charge, the current, and finally conduct the electricity. So both the melting point and the electrical conductivity increases from sodium to magnesium to aluminum. This can be explained by the number of electrons each metal donates to the sea of delocalized electrons. This is how you're going to answer these questions. Even if it's not for period 3, if it's for period 2, or maybe 3 elements from period 4 or period 5 or any other period have been compared, you are going to answer in the similar way, since any element from group 1 is going to lose 1 electron, or group 2 is going to lose 3, group 3 probably would lose 3. So that's how that works. So for most of the examples from group 1 or 2, you actually answer in the same way. And since we are talking about it, you can see Na positive, or since it's not written over here, if we were to talk about magnesium, it would have been Mg2 positive, or Na positive, or Al3 positive. So you understand the number of electrons they are actually giving to or donating to that sea of delocalized electrons. So this makes the metallic bonding in aluminum stronger, as the electrostatic force of attraction between its 3 plus ions and a larger number of negatively charged delocalized electrons holding the giant structure together, and they're stronger. So of course, we do understand that the metallic forces or the metallic attractions are going to be strongest in aluminum, stronger in magnesium, and least strong for sodium. Since they're all strong, we still stick to the word strong, but we use the adjectives to compare them properly. There are more delocalized electrons available to drift through the structure when aluminum metal conducts an electric current, making aluminum a better electrical conductor than either magnesium or sodium. I hope you get the point. Moving on, this is how it goes for melting point. Okay. So for melting point, continuing, the change in melting point across a period reflects the type of structure and bonding. As we go across a period, the metals have increasingly strong metallic bonding and their melting point increases. In period 2 and period 3, the group 14 elements have giant covalent structures, so have very high melting points. We're talking about carbon, we're talking about silicon, uh, specifically if we're talking about period 2 and 3. And if we're talking about carbon, you can consider diamond as an example. If you're talking about silicon, you can consider SiO2 silica as an example. So that's how we talk about them. And since both of them are giant covalent structures, they're not molecules. So never use the word molecules for them. Always use this word structure. You may use macromolecules term. That is the specific term to represent giant covalent or giant macromolecular structures. Okay, so they have very high melting points. If we talk about groups 15 to 18, most of the elements have simple molecular structures, so they have relatively low points, and of course, this is going to work like that. Now, since this happens to be in the form of this, and this is present as this, we can understand that the number of atoms combining these is different than what we had over here. The possibility of combining an octahedral or 8 octatomic uh, uh, molecules. So, of course, uh, small rise. I hope you get the point. Okay, so the element at the center of period 3 silicon has the highest melting point because of its giant molecular structure or giant covalent structure, macromolecule, silica. Each silicon atom is held to its neighboring silicon atoms by strong covalent bonds. However, the electrical conductivity is much lower than the metals at the start of the period because there is no delocalized electrons free to move around within its structure. Silicon is classed as semi-metal or a metalloid. Okay, specifically speaking, I haven't considered Graphite as an example for period 2 for giant covalent structures from elements from group 14. That's because of the reason if we're talking about electrical conductivity, it's going to behave a little bit different if we're comparing something tetrahedral. So it's better to consider diamond and silica since they have the same kind of structure to explain them. Now, the elements to the right of silicon are all non-metallic elements. They exist as small molecules, sulfur exists as S8, phosphorus P4, chlorine Cl2. The covalent bonds between each molecule are strong, but there are weak IDID forces between their molecules. We have already discussed these. So therefore, it does not take much energy to break these weak IDID forces between the molecules or melt the elements. So at room temperature, phosphorus and sulfur are solids with low melting points, and chlorine is a gas. Organic gas exists as single atoms. We call them monatomic molecules with very weak IDID forces between its atoms, even weaker than Cl2 or P4 or S8. So that's why the minimum. So that's how we explain all of these points as compared to one another. Okay. Now, keep something in mind. The jump between the presence of one or two electrons for the melting point. Also, group 1 elements are specifically low in their melting points and in densities, and for the rest of the periodic table, their properties from top to bottom in a group do not change in the same way. If we go from top to bottom for any group in the periodic table, the density increases, so does the melting point. But for group 1, this is the exact opposite. Instead of increasing, it decreases. So of course, there has to be a big jump in there, okay? Because group 1 behaves totally differently than the rest of the groups in the periodic table, which finishes up the melting point and the electrical conductivity patterns. Moving on to periodic patterns of first ionization energies. Now, we have discussed the first ionization energies in a lot of detail, all four factors that we have discussed. I've discussed them in the start of the chapter 2. So if we talk about period number 3 and their first ionization energies, I hope you can understand that how they increase from left to right in a period. Now, the general trend is in the increasing trend, but it's slightly different for metals and for non-metals. So yeah, something like this. Now, we have already discussed this dip and this dip previously in chapter 2. Since we're talking about 1s, 1, actually, I shouldn't be using the term 1s. Instead, just stick to S1. Since it's period number 3, so it's 3s1, S2. And as soon as we talk about PX1 or PY1 or PZ1, these are the ones. Then we start filling PX2, PY2, and PZ2. That's how we fill electrons. So for S's, it's different. For single unpaired electrons for the P's, it's different. And when we have the paired electrons in P's, it's different. Though the trend stays increasing, but there are two dips, and that is because when you move from S to P, unpaired electrons, and from P to P, unpaired to paired electrons, we get the dip. Since they have been previously explained, so that's why I was trying to explain them a little bit quickly. Okay. There is a general increase in first ionization energies across the period because the increasing nuclear charge and decreased atomic radius makes the attractive forces between the nucleus and the valence electrons greater. Remember, the group 13 and group 16 elements may not obey this rule. We have discussed this before. In general, the first ionization energies increases across period 3. As the positive nuclear charge increases, electrons are successively filled in the third quantum shell. As electrons are in the same shell, the shielding effect remains the same, is almost similar. There's small dip between Mg and Al and P and S. That's between group 2 and 13, and group 15 and 16, of course. And the same pattern appears in period 2, the same groups, different elements. And the explanation is given in section 2.6, which I've just repeated, applies here in 2. So if you look at period 4, now since this hasn't been discussed yet, but as you can see, they have taken out a specific portion of period 4. They have considered all the P elements. They haven't considered the S elements, since you can't see the potassium and calcium over here. So I hope you understand they're talking about a specific part for it. Okay. This finishes up 10.1 and 10.2.